Take a look at 4.8. So in 4.8, we're going to deal with our transformations. Now, overall, there are going to be 4 types of transformations we're going to talk about. However, we're only going to do 3 of them today. The 3 we are going to do today are what are known as your congruence transformations. Because, for example, in the opener, we talk about a reflection. If we take this triangle ABC and we reflect it over the x-axis, and we call it triangle DEF. So there are my 2 triangles. If I take my 2 triangles and I compare them, if all I'm going to do is reflect my triangle ABC over that x-axis, that new figure you create will be the same exact size as the old figure or the original figure you had. So are these 2 triangles congruent? Yes, they are. Now, as I mentioned, we are going to be doing some different transformations, right? And that's what we'll look at here today. What a transformation is, it is an operation that moves or changes a geometric figure in some way to produce a new figure. So, for example, we can take this triangle ABC and we can start to move it left and right. We can move it up and down. We can rotate it around. And those are all different things we're going to use. Last year, you learned them as maybe a slide, or you learned it as a flip, or you learned it as a turn or a rotate. Those are different terminologies, but it's the same idea. The new figure that you create is known as the image. It is a new figure that's created after a transformation. So maybe we take some triangle ABC and we do something to it, right? Maybe we'll take this triangle here and we're going to move it right 3 units, and then we're going to move it up 1 unit. And all of a sudden we create this new triangle over here. Typically we will call that triangle A prime, B prime, and C prime. That way you know what points match up. A went to A prime after that transformation. B went to B prime, C went to C prime. That idea of moving it left and right and up and down is what is known as a translation. A translation is we move every point of a figure the same distance in the same direction. So we're going to take all of our points here. We'll take points A, B, and C, and we'll move them all. Maybe we move them right 8, and then we move them up 2. Then we have to move C right 8 and up 2. And then we have to take A right 8 and up 2. Right? That's what a translation does. It moves every point of the figure the same distance in the same direction. The second one we'll look at then is known as a reflection. It's what we talked about in the opener. Right? It's when we use some line to create a mirror image of the original figure. Now, for our sake of argument, all we are going to do today is going to be something like your y-axis or your x-axis. That's what we'll look at today. Down the road, we'll venture into this a little bit more. But if I wanted to reflect over the y-axis, maybe point B was 4 units to the right, then it needs to end up 4 units to the left. If A is 1 unit to the right, A prime ends up 1 unit to the left. Your last one then is your rotation. That's where we're actually going to spin our figure around. We're going to turn that figure about some fixed point. For our sake of argument, the point we are going to use is going to be the origin, because it's going to have a rule that we can follow. Right? And that's the last one that we will do today. taking a look at each one then, it wants to know what is being presented here. So which transformation is this one? This is your rotation about that point P. Your second one here, if I take my unshaded figure and I bring it down to get my shaded figure, that is our translation. We went straight down in a straight path. And then your third one then, if I take all of these points on the left, there we go. If I take all these points on the left, if this is 2 to the left, it ends up 2 to the right. If it is 3 to the left, it ends up 3 to the right. If it is 5 to the left, it'll end up 5 to the right. If it is 2 to the left, as we said, it ends up 2 to the right. That is what is known as your reflection. Now, the three transformations we are talking about today are what are known as congruence transformations. We call them congruence transformations because we change the position of a figure without changing its size or its shape. So we're just changing where it is located. We're not changing what it looks like, or how big it is, I should say. Right? And then the last thing to go over here before we start looking at each of these transformations is what's called coordinate notation. Basically, what coordinate notation is, it wants you to be able to talk about how you are affecting the points of your figures. Right? You can talk about it in words. We're going to move something up 1 and left 2. Or how does that affect your coordinates? To move it left 2, that affects your x value. So you're going to be subtracting 2 from your x. To move something up 1, that affects your y. So we are going to be adding 1 to the y. That's what coordinate notation looks like. They want to know, how are you going to affect that x and y point that's there? So coordinate notation then, for your translation, says we are going to affect our x value, and then we're going to affect that y value. And how are we going to use it? We're going to translate it left and right. We're going to move it up and down. Left and right affects your x. Up and down affects the y. So in example 2, it says figure ABCD has the vertices. A is 1, 2. B is at 3, 3. C is at 4, -1. And D is at 1, -2. I want you to sketch figure ABCD and its image after a translation of x minus 4. So it says x, y is going to go to x minus 4. Y plus 2. So what are we actually going to do to our figure then? We are going to move it left 4 because it's x minus 4. And we are going to move it up 2 because it's y plus 2. And then they want to know, where will these points end up at? So for A prime, if we move it left 4 and up 2, we'll end up at -3, 4. For B prime, if we take it left 4, we're going to end up at -1. Up 2, we'll end up at 5. C prime, if we take it left 4, we end up at 0. We take it up 2, we end up at +1. For D prime, if we go left 4, we end up at -3. If we go up 2, we end up at 0. So there are our new points. Then I wanted you to plot those 2 points. Those 4 points. So here's where we end up at then. A, B, C, D is the original. A prime, B prime, C prime, and D prime is there. So that's the way translation works. For a reflection, okay? For our reflection, I want to talk about that real quick. So if I take point A and I reflect it in the x-axis, right now I am 2 units up from the x-axis, so we would end up 2 units down from the x-axis. There's where A prime would be. At that point, -4, comma, -2. So when we go over the x-axis, the only thing that changes is the sign of my y value. If you wanted to instead go over the y-axis, we're 2 to the right, we're going to end up 2 to the left at -2, comma 1. The only thing that changes for flipping or reflecting over the y-axis is the sign of your x value. And that's what our coordinate notation is going to say. To go over the x-axis, we multiply our y-coordinate by -1. To go over the y-axis, you multiply your x-coordinate by -1. So in example 3, it says you are cutting figures out of paper. Use the reflection in your x-axis to draw the other half of your figure. So there's our original figure that they give us to draw our reflection in. There's what it's going to turn out to look like. And then we're going to write down those new points that we get. Which brings us to our last of our transformations. Right? Is your rotation. It is the hardest of the group. So we're going to talk about exactly how this works. So first thing that we need to know is when we go and we do a rotation, there are different degrees and different ways you can rotate. You can rotate both clockwise and counterclockwise. We're going to always go counterclockwise because that's the way the book does it for some reason. The other thing is we're going to go in increments of 90 degrees. So if I take this point 3, 0, and I rotate this 90 degrees counterclockwise, where we actually end up is at 0, 3. So the first thing that's going to happen is we are going to flip our x and y point. Notice 3, 0 became 0, 3. Now there is a second thing that happens, but you can't see it on just this one. So I'm going to go another 90 degrees. And now we end up at -3, 0. Notice how they flipped again. I had 0 and 3. Now I have the 3 and the 0. However, they threw this negative sign there because that's the second thing that changes. So step 1, you're going to flip your x and your y. Step 2, our new x, up it comes. Our new x changes signs. Right? So I'm going to do it, and I'll show it with the point 4, 3 then. To go 90 degrees counterclockwise, we'd end up somewhere right in here. I'm going to flip my points. So I'm going to have a 3 and a 4. And my new x changes signs. I'm going to do it again. So this was 90 degrees. If I wanted to do 180 degrees, I'm just going to apply that rule a second time. So I'm going to flip my points. And my new x changes signs. To go 270, I'm going to do it again. I'm going to flip my points. And my new x changes signs. So it'll be a positive 3, negative 4. To go 360 then, we do it one more time. I'm going to flip my points. My new x changes signs. And notice I should end up right where I started, because if you go around 360 degrees, you shouldn't change where you are. Now, as I mentioned, our rule of thumb is we are going to go counterclockwise if it is not specified. And then our rule, every 90 degrees you go, we're going to flip your x and the y, and your new x will change signs. All right, let's take a look at our examples then. Okay, it says JK, graph JK and LM. Tell whether LM is a rotation of JK about the origin. If so, give the angle and the direction. So here's point J. Basically, it wants to know, when you take point J, can you get to point L? Well, if we rotate point J 90 degrees, we flip our point, and our new x changes signs. Well, that got us to point L. So J did get to L. If we do it for point K, if I flip them, change the sign of the new x. Did that get me to M? Yes, it did. So it is 90 degrees, and remember, we are going in a counterclockwise direction. Take a look at your second example then. Here's your point J. Take it 90 degrees. Flip your point. Change the sign of the new x. Did that get me to L? No, it did not. Then go another 90 degrees. What if I go 180? Apply the rule again. Flip them. Change the sign of the new x. Still didn't get me there. What about 270 then? Flip them. Change the sign of the new x. And it still did not get me there. So no, this is not a rotation. Taking a look at your third one then. It says graph RS and TV. Tell whether TV is a rotation of RS. So, can R get to T? Go 90 degrees. Flip them. Change the sign of the new x. Didn't get there. Do it again. Flip them. Change the sign of the new x. Still didn't get there. Do it again. Flip them. Change the sign of the new x. Still did not get there. So your answer is no. Fourth one then. Can RS get to TV? Well, let's start with R getting to T. 90 degrees. Flip them. Change the sign of the new x. Didn't get there yet. Do it again. Flip them. Change the sign of the new x. Positive 1, negative 1. I got there. That's where I wanted to be. Then let's make sure S gets to V the same way. 90 degrees. We flip them. Change the sign of the new x. Not there yet. Hopefully it works here. Flip them. Change the sign of the new x. And that is exactly where I wanted to be. So it is a 180 degree rotation. Technically, we use a rule for counterclockwise. But if you wanted to say clockwise, if you go 180 degrees either way, you'd end up in the same spot. Brings us to our last problem. It says the notation of x comma y goes to x plus 1, y minus 6, describes your translation of triangles PQR to triangle XYZ. So show that triangle PQR is congruent to triangle XYZ to verify that it is a congruence transformation. So there's my points for triangle PQR. If I am doing x plus 1, I am going to take it right 1. If I am doing y minus 6, I'm going to go down 6 to get triangle XYZ. Or you can subtract your points off. Minus 1, minus 6. Minus 1, minus 6. Minus 1, minus 6. To get your new points. So here are our two triangles that they want us to find the length of. PR is easy to find. It's a horizontal line. It is 3. XZ is a horizontal line. It is 3. Now, as a quick reminder, you can use your slope to find your length. So that's what I'm going to do right now. My slope of PQ goes up 2, goes right 1. So it's a 2 over 1. 2 squared is 4. 1 squared is 1. And we take the square root of it. So PQ is the square root of 5. For QR, we go down 2, and we go right 2. So it's a 2 over 2. 2 squared is 4. 2 squared is 4. Put them together, and I get the square root of 8. So my three lengths for triangle PQ are PQ is the square root of 5. QR is the square root of 8. And PR is 3. For triangle XYZ then, XZ is 3. It's a horizontal line. XY has a slope of up 2 and right 1. So 2 over 1. 2 squared is 4. 1 squared is 1. So you get the square root of 5. For YZ, we go down 2. We go right 2. Negative 2 squared is 4. 2 squared is 4. Add them together and we get the square root of 8. So we have PQ congruent to XY. QR congruent to YZ. PR congruent to XZ. So yes, those two triangles are congruent. And that's how you show it. Right? If you didn't want to use your slope formula, as a quick reminder, your distance formula is here. And you can plug your points into that distance formula if you would like. Right? Here's your homework tonight. Now, you'll see numbers 9 through 12, I am changing the directions. They ask you to plot the original shape and the new shape. Instead, all you need to do is write your new coordinates for X and Y. You do not need to plot them. You can if you want. If it'll help you, you can do that, but you do not need to. So there's your homework that you see there. Please let me know if you have any questions.